to section 5.1. This is kind of our brave new unit that we have about Laplace transforms. It is a tricky concept, and we're going to just dive right in so that way I can define what exactly a Laplace transform is for you. Now, if we were in class, we would watch a Khan Academy video to introduce this, and I will link it in the lesson so that way you can watch it. I think there are some parts that are useful. I'm going to break down some of the stuff from that video and then, allow you to just kind of go and watch it for the rest. So the definition of a Laplace transform, we use a capital cursive L here to represent a Laplace transform, and we use curly braces, and we say the Laplace of some function f of t becomes a capital F function of s. Now, what we're doing is we're taking a function of time and we're performing a transformation to make it a function of s, which is frequency. And so this is a very common thing to do in engineering applications, which you won't have to worry about as much here, but just so you know where those variables are coming from. So what a Laplace transform allows us to do is, instead of just transforming constants or variables or things like that, we are taking and transforming functions onto another set of functions. So another way that you will see this, and I will just write it off to the side here. So also, you could see the Laplace using y's instead of f's. So some people will do the Laplace of y of t, and it becomes uppercase Y of S. And I definitely have done some examples that you will see using Y's instead of F's. Now, this probably doesn't mean a whole lot. And then let's go ahead and define what this Laplace of f of t actually is. So maybe it does mean something. In order to perform a Laplace transform, this is equal to the indefinite integral from 0 to infinity of e to the negative st times f of t dt. Don't want to forget that f of t in there. So this is the definition that we are going to follow to perform our Laplace transforms. And then there will be a table where, instead of having to do this indefinite integral every time, you have a quick reference table to get from the pre-transform into the post-transform here. The video does cover the Laplace of just the constant 1, and I do encourage you to watch that because we want to know what happens when we take the Laplace of constants for sure. But I am going to let you watch it for that one, and I'm going to go ahead and skip past it and do the Laplace of e to the alpha t. So looking at what happens when our function is e to the alpha t. So using the definition, this is the improper integral from 0 to infinity of e to the negative st times e to the alpha t dt. And now this is an improper integral for a reason. We can't evaluate an integral at infinity. And so what we do is we take the limit as a goes to infinity, and we evaluate the integral from 0 to a. Now I'm going to go ahead and use some properties of exponents here to combine this and make this e to the alpha minus s, just flipping those, make it a little easier. So e to the alpha minus st dt. And when I go ahead and integrate here, that means that I am evaluating the limit as a goes to infinity of 1 over alpha minus s e to the alpha minus st. And then we're going to evaluate that from 0 to a. All right, so I'm going to go ahead and leave that limit on the outside here, and we're going to go ahead and evaluate at a and at 0 and see what this looks like for us. So this is going to be 1 over alpha minus s e to the alpha minus s, evaluating that, because remember this was dt, so evaluating that t as a, would be the first part, minus 1 over alpha minus s. We are going to get e to the alpha minus s times 0, which would be e to the 0, which is just 1. So essentially, as this all goes to 1, we are left with just 1 over alpha minus s. So basically, looking at this first part here where we still have our exponent, we need for it to be true, we need this to be true where s is greater than alpha. Okay. The reason for s to be greater than alpha here is that if oh my gosh. Hold on, let me think about this. Let me pause real quick. Okay, sorry for that quick blip. So we need s to be greater than alpha because here we're looking at this term evaluates a in your exponent. If e goes off to positive infinity, where a is headed towards infinity, then there is no limit. It doesn't converge. And so, in that case, we wouldn't, in that direction, we wouldn't have a limit. If s is greater than infinity, which would mean that alpha, alpha minus s is negative, then what happens here is alpha minus s is negative. And this is evaluating then what happens as our limit approaches negative infinity. Towards negative infinity, there is in fact a limit, and that limit is 0. And so as long as this is the case where s is greater than alpha, then my limit for this will in fact be 0. For this over here, we have 1 over alpha minus s left over, and there is no a, so we don't have to worry about evaluating a limit. It was really just this first term right here. So what we get for this is negative 1 over alpha minus s, or, if we wanted to rewrite that with a little bit less negative here, we would say 1 over s minus alpha. Okay, when it is the case that s is greater than alpha. So this is our Laplace transform for e to the alpha t, is that we get 1 over s minus alpha. Notice how this goes from a function of t to a function of s. And so that's our first Laplace transform. We're going to do the next one. That was that one right there. The next one down here is the Laplace of t. We're going to do this together, and then you are going to submit a couple that you do on your own based on this. So using our definition here, remember that the definition says we are going from 0 to infinity of e to the negative st times our function of t. So I'm going to go ahead and put that function of t, e to the negative st, like this, dt. And in order to do this, this means we are taking the limit as a approaches infinity of the integral evaluated from 0 to a. Okay, this is an integral that we have to do by parts, and so I will shortcut that for you. We won't go through and do that by parts together in these notes. I'm going to go ahead and just tell you what it is. So the limit as a approaches infinity of negative t over s e to the negative st minus 1 over s squared e to the negative st. And then we are going to go ahead and take that and plug in from 0 to a. All right, so the first part, I'm having real issues drawing infinities. Okay. The first part here, plugging in a, will look like this. Okay. And then minus, so let me do a bigger set of parentheses here and plug in 0, which will look like, this is a little easier because this is going to be 0 times e to the 0, which will just be 0. And then we are going to get minus 1 over s squared e to the 0. And so this piece here, since this gives us 1, will just be 1 minus 1 over s squared for that last piece right there. Okay, so we'll just leave that here for a second, and let's go ahead and take a look at this here. So if I evaluate what happens as a goes to infinity, here again are e to the negative infinity times s, so the s becomes irrelevant. E to the negative infinity, the limit of that is 0. And even if we plug in a really gigantic number here for a, as a approaches infinity, it won't matter because the exponential piece overrides everything. So this limit is equal to 0. And then we'll see that the same thing happens right here because our exponential piece overrides everything. So the limit of that also 0. So what we get when we approach this limit as a goes to infinity, 0, 0, and we're left with this little piece at the end right here. So this just leaves me minus a negative 1 over s squared, which is a positive 1 over s squared. Okay. Now, here's what I would like you to do. We skipped the parts integration here, okay? I would like you, and submit it as, today's assignment, to figure out what does it look like if you take the Laplace of t to the nth power. Okay, now it's going to be very similar to what we did, and in fact, I'll do the definition piece here with you. So this is going to start out like this. Okay, that's your integral right there. You're going to evaluate the limit as a goes to infinity of our integral from 0 to a of t to the n e to the negative st dt. And I would like you to finish this problem here, figure out what this looks like by integrating by parts, evaluate the limit, and tell me 2 things in your solutions that you submit. What is the Laplace of t to the n equal to? And then I want you to apply that to a couple of things here. I want you to apply to the Laplace of t squared. What happens when n is equal to 2? What is the Laplace of t to the third? And what is the Laplace of t to the fourth? Just to start building up that table. And again, we're not going to, have each of these in there individually, but just to make sure that we can evaluate when we do have these higher power values of t. Now, I know you're resourceful. You can totally look up what this will end up being, but I want to see your worked out integration here. And I want to see that you know how to apply this formula to each of these. So this is what you're going to submit, basically what's on my screen right here, in order to get your points for today. Good luck with that. Let me know if you have questions.